right, so Suchitra, congratulations on being awarded the Young Alumni Achievers Award. Um, and it's great to have you here. When was the last time you were here?
I think about 5 years ago we had a batch reunion here. So yeah, it's been a little while. I haven't been to the new side of campus before. So yeah, it's interesting.
Great to have you here. Um, and so, how would you describe your journey after IIMA? I mean, it's an interesting route that you've taken after from management into physics.
Yeah, so my undergraduate was in physics. It was a liberal arts college, but I did physics, and yeah, I think I enjoyed physics, but I did not want my entire worldview to be just physics. And so I thought I would try doing something that was very different from physics so I'd see how the real world worked. So yeah, I ended up in Ahmedabad. And I think I learned like quite a few things about the real world, especially I think to do with looking at things from a strategic point of view and talking. So I worked with a consultancy for a bit after IIMA. I worked with TSMG as a management consultant. And the concept of going into an organization, talking to various people at different levels, and then arriving at some kind of synthesized view of it, and then being able to communicate to the organization what it is you wanted to convey. I think all of those things are quite high level skills that are now proving very relevant to my career, which is very different. So after a couple of years in a management consultancy, I then switched to do a PhD in applied physics at Stanford. Um, I think actually I don't think at that point I knew I was going to become a physicist. I think my main motivation at that point was to go back to university. So yeah, so I think the main motivation was I wanted to be in an area where I was discovering new things. And I think when you're working in area of strategy with the real world, then a lot of it has to do with acquiring information and then structuring it in certain ways, synthesizing it in certain ways, communicating it. And I think I wanted to be at the edge where you're accessing knowledge that is not known, so it's beyond the known. And I think I wanted to be at that end of research and discovery, so that's why I ended up doing my PhD in physics, but I did not expect I would stay in physics. But yes, so I did a PhD at Stanford, and then after that, I moved to Cambridge, and I'm now faculty in physics at Cambridge.
So, do you think there's something that you took from here that helped you in your work in physics?
So I think so. At the moment, I am definitely passionate about researching the unknown, making discoveries, but I am also passionate about communicating physics well to non-scientists, about involving a different types of people in the doing of the physics, in cutting across disciplines like the arts and the sciences. And I think that kind of a bigger picture view of thinking that's not just restricted to physics. I think that was something that, having been outside physics in the business world, I am definitely much more conversant in the language of people who aren't physicists. And I think it makes me see with much clearer perspective how limiting the view is if one looked to the entire world through the lens of physics. And I think being at IIMA helped me with this kind of communication, this kind of straddling different areas, because of course when you're a consultant, you're constantly in one type of area or the other, in one sector or the other. It's not the one focus that you're pursuing. And so this kind of ability to synthesize knowledge from very, very different areas, I think at the moment it's not something I use just in physics, but very much in the area of making physics more accessible, making it more interdisciplinary, and having that overall strategic perspective of why is the field the way it is, and if we want to change it, how might we want to change structures so that the people in it changes, the way we do it changes, as opposed to kind of being locked into a very technical approach to doing physics.
So you, of course, work on a lot of different areas in physics, but you've uh, been called an explorer of quantum borderlands, right? So when did you sort of discover your fascination for quantum effects?
So as I briefly mentioned, one of the reasons I switched back to physics after an MBA was that I wanted to explore the unknown, to go beyond the limits of our knowledge. And during my PhD, I started discovering that actually doing research in physics, if you choose to do it in that discovery-oriented way, is a constant journey of discovery. And especially with quantum effects. So with quantum effects, the kind that I study, the idea is that a single electron behaves in a certain way. We largely understand how it behaves. But when you have a macroscopic ensemble of electrons, when you have billions and billions of electrons coming together, then you have effects known as emergent effects, which only occur on a macroscopic scale. So you can think of an analogy like shoals of fish or flocks of birds, and they have formations they come into only when they're in large numbers, and you would not see that if you had like one or two of them. And the idea is in a way similar, that when you have a large number of electrons, when you have an ensemble of electrons, they start behaving as a giant wave instead of individual electrons bumping into each other. And when they behave as this macroscopic quantum waveform, the physical properties are completely different from that of the single electron. They don't resemble a collection of single electrons any longer. It looks like something completely different. It's like an M.C. Escher painting or something, where you start at one end, where you start with birds, and then this collective of birds evolves, and at the other end, it looks like a collection of houses or fish or something else. The idea being that when they come together, they form this collective ensemble, the properties of which are diametrically opposite from individual electrons. And this to me was incredibly fascinating, particularly because this is beyond the realms of our current theoretical understanding. So theoretically, we can understand what one electron does, what two do, but because at a macroscopic level they behave completely differently, that's beyond theory. For instance, one of the effects I work on is superconductivity, which is materials that can carry electricity without any loss at all. So if you took a circle of wire made of superconducting material, cooled it down below the superconducting temperature, almost magically it will completely lose all resistivity to the flow of electricity, and you put a current through it, will flow for the age of the universe, will flow forever. So if you think of electrons individually, they would be bumping into each other, bumping into the lattice walls in the crystal structure. But when they all coalesce into this giant quantum wave, it's like they begin to become aware of each other, and they all begin to flow in completely coordinated motion with no loss of energy by this bumping into each other and bumping into the crystal walls. And so this is one example in which these quantum emergent effects give you behavior, superconductivity, that is completely different from the kind of behavior that you would have seen with single electrons. But what particularly fascinated me was that almost all of these effects are beyond our current theoretical paradigms. And so I do experiment, and it's incredibly exciting to do an experiment and discover an effect that is not what it's supposed to do according to the textbooks. And that's what I enjoy most of all. I'm not, what excites me isn't, oh, you take a theorem and then you prove a theorem, because, well, you kind of knew that was going to happen. But what I enjoy is when it doesn't do what it's supposed to do. And with quantum macroscopic effects, that is what you're dealing with all of the time. So you do have some expectation from what you thought. You might see even beyond existing theory, but almost always, every time I do an experiment, the results are never what I thought it would be. And that's what I find very exciting about the quantum space.
And are there other areas among the other areas that you are working on in physics? Do you find working on those help you with the your exploration of quantum effects?
So actually, almost all of the areas I explore are to do with this space because this is what excites me the most. So the tools I use can be used equally. So in amongst materials, the ones in which electrons interact more weakly with each other, so you can still be thought of a collection of individual electrons, and they're the ones with the electrons interact strongly with each other. And then you need to think of them as an ensemble of electrons. And those are known as strongly correlated electrons, or interacting electrons. And I almost exclusively work with that category of materials where you expect to see unconventional quantum effects, because that is what I find the most exciting.
In 2015, you made an interesting discovery with samarium hexaboride, right? So could you tell us a little bit about what that was and how did it come about?
Yeah, so one of the tools I use to do experiments is to trace the trajectory of electrons. So as an electron flows, they flow on, they map out a surface. And so you can trace the geometry of the surface, this trajectory of electrons. And typically, we expect electrons to flow in metals or in conductors. Whereas in insulators, you expect the electrons to be stuck in one place, so they don't carry electricity. And that's why materials are insulating as opposed to conducting. So we were studying this material, and we go to very high magnetic field laboratories to do these experiments, because in order to study the electron trajectories, it's like a magnifying glass. If you use a very big magnet, you're able to map out these trajectories much better. So we were at a high magnetic field lab in Florida, and the material we were actually studying was samarium hexaboride, and this is actually an insulating material. So if you put current through one end, it doesn't come out through the other end. But it was thought that, okay, maybe the surface of this material conducts a small amount of electricity. So what we wanted to see was what the trajectory was of those electrons on the surface, which do flow, whereas the electrons in the bulk, the volume of the material, don't flow. They're stuck in one place. So this is what we were measuring, and we did these experiments trying to measure electrons flowing through the surface, and we didn't see anything. So we tried and tried, we didn't see anything, and at that point I was like, okay, my student has to get a PhD, let's, just do another measurement that at least he can write up saying these are the things we studied, even though what we saw was not really what we were looking to see. So then we did another measurement that didn't just access the surface of the material, but that accessed the bulk of the material. And so we put that in the magnet and started measuring it. And it was very, very odd, because we could see signals of the electrons executing trajectories as though they were moving large distances and mapping out this surface, which was completely counterintuitive, because the electrons in this material are not moving, because if you put current one end, it doesn't come out the other end. So the electrons are stuck in one place. But yet, when we do this measurement that enables us to look at the trajectory of electrons, it's as though they were mapping out these large trajectories. So it's like these electrons were doing two different things that were diametrically different, which was schizophrenic in a way. Like, how could the one electron both be stuck in one place and be moving large distances and mapping out trajectories? So usually when you find something you aren't supposed to see, the first thing you wonder, you've done something wrong. So then you check to see whether you accidentally, there was some contamination of some conducting material, and there wasn't. And then we check to see if like one of the wires had come loose, it hadn't. And so then I called my colleague in Cambridge and say, this is very odd. We're seeing like electron trajectories in an insulator. And there's silence for a bit. And then he says, you do realize that's impossible. And I'm like, but we're seeing it. And I think that's one of the things that I've definitely learned through doing experiments is that there's no impossible. There's just like what you thought to be the case from your existing body of knowledge. And were that to be the only physics, then sure, it appears impossible. But if you do an experiment and that's what your experiment tells you, you have to trust your measurement. And all it means is that your idea of the theoretical conception is just incomplete. And over and over again, that's what really excites me when you do a measurement and you're like, that's impossible. But of course it's not. It's just showed you that what you thought you knew was not right after all. So we're still trying to understand the theory behind how these electrons could behave in such a schizophrenic way. We don't know as yet. One possibility is that when one has this ensemble of electrons, they're not behaving like individual electrons anymore, but maybe they're behaving as though the charges behave separately from the spins. Each electron has a spin and a charge. So maybe they're behaving as though the charges don't flow, they're stuck in one place. That's why electricity doesn't flow. But maybe the spins can move, and that's why it looks like you're seeing trajectories, although the charge isn't moving, and so you're not seeing a flow of current. But we're still trying to understand the physical origin for such an effect. But yeah, that was a very exciting moment of discovery.
So could this mean potential discovery of a new building block of matter?
So actually, yeah, it's an interesting question. So I think that there's sort of largely two ways of looking at physical properties. One is to say, let's understand physical properties by breaking them down into the smallest constituent particle possible. And that is a reductionist way of thinking, where you say, in order to understand the big picture, I break it down to the smallest elements. And when I understand the smallest elements, I can then understand how they fit together to form the big picture. The way I explore it, and a different sort of route to exploration, is to instead say, when a macroscopic ensemble of electrons comes together, they don't behave anything like the constituent particles do. So instead of trying to break it down to the elements and understand those, let's instead focus on the behavior of the macroscopic ensemble and identify phenomenologies, patterns of behavior, and in that way try to, almost in a way, invent hypothetical building blocks that you can describe this collective ensemble with. So what it's saying is you start with electrons, but by the time they all coalesce into this giant quantum wave, you can no longer think of them as individual electrons. But it could be that to understand this giant quantum wave, instead you think of a hypothetical building block, which the only utility is for us to wrap our heads around that kind of behavior. So you say, oh, hypothetically, if I had charges behaving separately and spins behaving separately, I could build a model to explain this. It doesn't mean in reality charges are separate and spins are separate. It just gives you a tool to think of what bits, if you put together, could give you this kind of behavior. The reason being that we are much more adept at thinking of like small bite-sized bits that you can put together to create this quantum ensemble, and we're less good at, we don't have models to describe these like macroscopic ensembles, but maybe in the future we will. But right now we still think of them as some kind of building blocks. So in that way, yeah, it could be that we found this new phase of matter that needs to be thought of in terms of different building blocks to ones we've known before. So yeah, that is an interesting possibility.
And does this have any implication for uh, energy security or something similar?
Um, yeah, so as I mentioned like a little while earlier, one of the areas I work on is superconductivity, so materials that carry electricity perfectly. And those materials do have tremendous import for energy transmission because at the moment we only need to transport electricity short distances because there are coal plants, there's oil refineries, and these are fairly um, well populated in most regions. So you don't have to travel long distances with the electricity. But once we do start switching to alternative energy, so wind power, solar power, hydropower, these are quite restricted geographically, and they are not typically near where the most densely populated urban areas are. So we do need to carry electricity. And so to do that, we do need to switch to different forms of transmission because current DC electrical cables can only carry electricity over short distances. And so, in order to be able to transport electricity over long distances, one has to move either to high voltage DC cables or superconducting cables, which have zero loss, or the high voltage DC cables have very low loss. And so, one of the quantum effects I'm studying is indeed the physics behind superconductors, because if we want to make better superconductors that are more economical and practical to use as these transmission cables, then so they are already used in transmission cables, but at the moment the lengths are maybe tens of kilometers long, but ultimately we want to scale up to thousands of kilometers long. So we need to find better superconductors. And in order to do that, we need to understand the underlying quantum physics better. And so in our quest to understand superconductivity, we are trying to understand the physics behind it, which is very different from the physics of conventional metals or even conventional superconductors, which are like metals but better. But these don't even seem to be like that. They seem to be completely different. And so one of the possibilities that if these building blocks of spin flowing differently from charge that we explored in the samarium hexaboron might be a possibility, those could be carried across to superconductivity, in which we ask the question, why is this form of matter so strange? And then we could ask, is it because we need to think of it in terms of these different building blocks of matter? And in that way, the more exotic quantum effects we discover, and the more possibilities for these different ways to conceptualize the building blocks, then we could use those tools to possibly understand superconductivity.
So your passion for physics is obviously coming through, and you are also passionate about popularizing science, and you do soapbox talks. So, what do you think should be done in the Indian context to popularize it even more?
Um, I think that one of the areas in which I think science could do a lot better is to introduce the notion of discovery much, much earlier. So I think when children are taught in schools, there is this idea that there's a body of knowledge that you are acquiring, and tests are on how well you have retained this body of knowledge. It's as though the answers are all known, and you have these closed-ended problems like solve this problem, and then the answer is at the back of the book, and then your goal is to get this answer at the back of the book. In reality, research is about discovery, and it is about pushing the boundaries of knowledge, because actually the infinity of things we don't know is far, far more vast than the tiny subsection of things we do know. And I think we're doing very well at attracting the subsection of people who really like solving difficult mathematical problems, or solving problems where you know the steps to do, you've learned what to do, and then you reproduce the steps and you get the answer, and that is considered to have done well. I think we're losing people who would be much more excited by the concept of discovering new things and it being open-ended, where the point of learning is coming to concepts rather than a tool for solving something. But the idea of a concept being, it could be things like, why does an apple fall, or what velocity does a rocket need to be shot at to exit the Earth's atmosphere. So, these are questions that we are taught, and then we are taught how to solve them, and then we solve them and get an answer. But concepts have to do with, if I translated this question into a completely different context, would you be able to recognize what are the physical principles at work? And would you be able to think for yourself on encountering a new situation that didn't have to do with rockets or apples, but had to do with something you encounter in everyday life? Would you be able to think about it physically from the concepts you've learned and then say, oh, I understand the point of doing physics. The point is to be able to think about physical phenomena we're surrounded by and think, oh, these are the forces at play, and be able to break it down into, oh, so this is the effect of gravity, or this is the effect of friction, and recognize where it is all around us, what it can be used for, what is the point of studying what we're doing, in a very hands-on way, in a much more exploratory, concept-driven, discovery-oriented way that is not just, I'm solving problems someone has told me to solve, applied to a context that has been predefined for me, that has very little connection to the world around me. But this is completely the opposite of what science should be, because in reality, it is about the physical world that is all around us. That is what we're trying to explore. It is what we're trying to explain. But what students are taught in schools is somehow diametrically different to this. So when they come to research, it's almost a shock that there are no predefined answers. And I've had PhD students who do very well in an Indian context suddenly come to a PhD and expect me to tell them what to do. And then I say, but it's your PhD. If I knew what was to be done, it would not be research. This would have been done. But they still find it very difficult to shake the notion that, like, I'm some kind of seer who's going to tell them what to do and they'll do it and then this problem will be solved. The idea that they need to figure out for themselves what needs to be done, and there isn't necessarily a solution beyond one that they discover for themselves. This is a very, very difficult notion for quite a few people from this context, especially to grapple with. And I don't think it's necessarily just in an Indian context that this is a challenge, but I think universally this is something that I think needs to be improved.
So, what do you do to wind down?
I don't think I have a winding down mode.
You're involved with arts and a lot of creative
I
ventures.
I do theater, yeah. So I perform in theater, but I do it with equal intensity as I do physics. So yeah, I am involved in setting up a program at Cambridge to bring together the arts and the sciences. And the idea is that science is one way of knowing, but equally there are disparate ways of knowing, and the humanities and the arts are equally ways of knowing. And it is very powerful to come at a new idea, a new concept in many different ways, and they enrich each other. And so recently, I organized an exhibition to inaugurate a new physics building in Cambridge. And it was about Maxwell, who discovered electromagnetic waves. So the idea that Light, electricity, magnetism are all different forms of waves, but they interact with each other and communicate with each other. And this is the idea behind electromagnetic wave theory. And so for this exhibition, we had artists who were communicating with scientists to understand the bigger picture behind these concepts being explored, beyond what can be measured or captured by mathematical tools, which is what physicists do. And so, for instance, we had modern dance choreography in which there were dancers whose movements affected light falling on a solar panel. And so as the dancers moved, the light impinging on the solar panel changed, and according to that, the background music that we had also changed according to the dancer's motion. So it was the same idea of different forms of energy interacting between the dancers' bodies and the light and the sound. So this was in some ways a tangible exposition of a concept that is very powerful, taken in concert with a different way of looking at electromagnetic waves would be measuring them or describing them via equations. But it's very powerful, especially to a non-expert audience, to see it in a more intuitive way, as demonstrated via physical interactions, via dance, etc. And so that's an art-science interaction I'm building in, and that's a program we're launching at Cambridge. But apart from that, I also perform in theatre. And I do this in order to provide a foil for physics, which is very, very intensely cerebral. And so it has a lot to do with thinking and concepts. And in a sense, physics is so strongly cerebral that you can do thought experiments, and thinking a thing takes you quite a way towards understanding a thing, and takes you quite a way towards being able to grasp the physics of something. A lot of it is thinking of concepts and making progress in that way. What I really need to balance that with is using other faculties. And theatre, I find even more challenging than physics, because you can't think a thing and it be reality. So, for instance, if you're a character in a play and you read the lines and you come to the conclusion, oh, this character appears to be angry in this encounter. And so if you were doing it in a physics sense, you would think, oh, this character needs to be angry, so I need to perform it as though the character were angry. But in reality, this is not how people behave, and this is not how physically realizing a state of emotion or a state of being is. In reality, people don't decide to be angry and then act angry. In reality, people respond to a stimulus. And so when you're performing, actually being in that moment and embodying a response to what is happening is completely different from your idea of what is supposed to happen. So you can't just have everything in your head and think something and expect that you can perform the thing you thought, and that would be the same as actually being present in that moment. And so I find theatre very, very powerful because it requires me to be physically present in that moment and use my other stimuli of responding to other people, of listening to what someone is saying and responding to that. And I think this is also something most of us don't do very well, to listen, especially if we're in these achievement-oriented fields. We think we know everything. And so we're so used to telling people our idea of a thing that we don't listen enough. But on stage, unless you listen to what someone's saying, if you just say your lines like you've decided how to say them and you're going to say them, that would be terrible, terrible performing, because it would be completely unconvincing, because the person watching it is expecting an organic interaction. Someone has said something to which you respond, because that's how people behave in real life. So unless you're able to not just think of, but actually physically be present in that moment and be present in the interaction you are having on stage in the reality of that moment, you are completely unable to be convincing in any kind of way, because people watching they may not know, how physical objects behave, but they know how people behave. And they know if you're being something that's real or you're being something that's acting. And this is what I find very, very compelling about theatre, is the ability to use those different faculties, but very much develop empathy, communication. It's to do with people. It's to do with rapport with people. And in some sense, I think it's a great pity that this is often almost culled out of science in a way, as though it's some analytical tool that is neutral somehow, that has no human interaction involved, but we could be machines doing these experiments and coming up with these theories, and that would solve everything. Like, if we had a more superior machine doing it, that would be better than if people were doing it. But I think in reality, we are human, and the science that we do is a product of our creativity, of us being who we are as individuals. And I think doing things like theatre, for me, builds that human connection of being able to recognize impetuses other than merely ones that are mechanistic in a way, or analytical. And so that's one of the things that really draws me to theatre. But also, more recently, we're setting up a new theatre company that's specifically to introduce more diverse forms of theatre. Because, like with everything else, I enjoy being at the borders of things and going beyond what is known. And so at the moment, I view theatre, especially, so I think actually Indian theatre is very, very rich, right? There's different forms of storytelling. But when it comes to English theatre, it is still very restricted in the kinds of stories that are told, the kinds of subjects that are dealt with. And it's the same elsewhere. So in Cambridge, for instance, theatre is very much mainstream with certain stories that are told, like Shakespeare or Oscar Wilde or something. And I would very much like to bring different traditions of storytelling, of different geographical regions in the world, different types of narratives that are usually unheard in the mainstream, that are present in diverse regions, among diverse demographics, and really bring them to the fore and bring them into mainstream, and not just have them. And this is like in India, for example, it is something that is a big tradition. Like in the South, there is a tradition of telling stories, and interspersed with dance and interspersed with moral expositions. But there's like a big chasm, as it were, between those very, very rich forms of theatre and bringing them into a more mainstream performative element. And so that's something that a group of us are trying to launch in Cambridge, to have the bringing together of all of those different types of narratives being performed, to add a richness to it that wouldn't exist if you only did the one form of theatre.
I can see that doing this itself is your relaxation. And you enjoy it so much. Well, it was great talking to you, Suchitra, and we're very proud of your success. And congratulations again.
Thank you very much.